Alright, this is video lesson 11 of our semester-long sequence of videos in basic circuit analysis. So a question for you, how useful is a circuit that is built only on resistors, voltage sources, and current sources? And the answer there is not very useful. And so here we're kind of turning the page and we're going to, or turning the corner rather, and we're going to start looking at some new devices, capacitors and inductors. And so here I have two circuits that I built on some cardboard, and the circuits are identical, but one has a capacitor and one doesn't. So let's look at the one that does not for right now. So this guy has an on-off toggle switch and an LED. We'll just call that a light. It's got a light and a switch, and behind it is battery pack and a resistor there. Okay, so it's got a switch, and when you switch it on, the battery powers the light through a resistor. Now, I also have this one, which is the exact same thing. Okay, it's got the resistor, it's got the toggle switch, it's got the battery, it's got the light, and this has quite a big capacitor here. This is a capacitor. Alright, so I'm going to turn the lights off, and I want to just show you the difference in the two circuits. So there's one with a capacitor, one without. We'll start with the one without. Okay, so I'm going to turn this guy on. And now observe when I turn it off, it turns off almost instantaneously. So let's do that again. So I'm going to turn off on 3, 2, 1, off. Alright, next circuit with the capacitor. Here's the capacitor. Turn it on. There it is. Oh, it's got a short circuit somewhere. There we go. Now I'm going to turn it off in 3, 2, 1, off. Alright, so hopefully you've seen there that this one fades. It takes a while before it's completely gone. The light's completely gone. Okay, so the goal, to put it in simple terms, the goal of really the remainder of the semester is to understand why the capacitor has this effect, and also its counterpart, the inductor, why the inductor would do something similar. Let's get to it. So capacitors you've seen before from physics, and in particular I want to just briefly discuss the parallel plate capacitor, which is exactly what it sounds like. You've got two metal plates that are parallel to one another. And they are initially uncharged. So for every positive, there's a negative as well. So we have a net charge of 0 on this plate, and a net charge of 0 on this plate. And separating the two plates is a dielectric material, sometimes an insulator. So for this example, we'll just say there's air there. Okay, air is our dielectric material, and each plate has a cross-sectional area A and a separation distance D. Now, this is nothing too groundbreaking here for right now, but if you connect a voltage source V to the plates, so here I've got the positive side of the voltage source connected to the left plate and the negative side of the voltage source connected to the right plate, well, the negative charges on the left plate are going to be attracted to the voltage source, and the voltage source is going to push them away from its negative side. So the effect you have here is that the negative charges leave the plate on the left and get pushed over here. Right? And similarly, the positive charges on this plate are attracted to the negative side of the battery, and then it pushes the positive charges over this way. Right? So now each plate has a net charge, and we'll call that net charge in an absolute value sense, we'll call that Q, meaning Q is positive here. So this has a charge of positive Q, and this has a charge of minus Q. Now, when you have two charges separated by an insulating material, then you have an electric field that is established. And in this case, the electric field points from left to right, and the electric field always points from positive to negative. So here's our electric field, E. So if I were to drop in a negative, we'll say a positive charge, positive. That's a positive charge. Hang on, let me draw that a little bit bigger. Okay, it would be repelled from this plate, and it would travel from the positive plate to the negative plate. Right. So in this case, and for this device, the charge on each plate Q is proportional to the voltage that you apply across the capacitor. Okay, they're proportional. So if you have 0 voltage there, then like we started this thing with, you have 0 net charge on each plate. And if you double the voltage, then you double the charge, etc. So the proportionality constant, we use this capital C. So we say Q equals C times V. And that constant of proportionality, of course, is Q over V. And so the units here, well, the units of charge is a coulomb, not to be confused with this C. And the unit of voltage is, of course, volts. So 1 coulomb per volt, we call that a farad. Farad, named after Michael Faraday. Okay? And this constant of proportionality, C, we call that the capacitance. So the capacitance is measured in farads. 1 farad is quite a bit. A 1 farad capacitor would look like a monster energy drink, maybe like a foot tall. It would be a big cylinder, maybe a foot tall. These types of capacitors are used in car sound systems, but you will normally see capacitors in the range of microfarads or nanofarads or picofarads or millifarads. These are much smaller. Okay, I think the one on the board that I showed you at the beginning of this video was 100 millifarads, and even that was a little bit big. That was kind of 2 inches tall, maybe. All right, so we've got our capacitor, and in this course we're not going to be interested too much in what happens inside the capacitor. That's physics, and I'm not going to say really any more about what is happening inside the capacitor other than the capacitor's job so to speak, is to store energy in its electric field. Okay, so we said we've got this orange positive charge. So if I was able to physically grab that positive charge and place it into the electric field, it would move as soon as I let go, and it would go from left to right. This is exactly analogous to the Earth's gravitational field, which points downward, right? And if you were to release a basketball, let's say, it would go from top to bottom, right? So in that sense, the Earth's gravitational field is storing energy. It's storing potential energy, gravitational potential energy, the potential to move. Similarly, the capacitor is storing electrical potential energy, the potential for a charge to move. All right, but other than that, we're not too interested in what's happening inside the capacitor. The capacitor, its circuit schematic symbol looks like this, and we are interested in when I connect the capacitor to a voltage source, a resistor, a current source, what happens to the voltage across the capacitor, and what happens to the current through the capacitor. All right, well, we have this equation. Okay, I'll put a box around it, and I'll label that as equation 1. So we have equation 1 for us, but this has got voltage. That's the voltage across the capacitor, okay? But it does not have current, and we're typically interested in current and voltage. So we've got charge, and charge is related to current in that current is the charge rate of change. So if I took equation 1 and I took the time derivative of both sides, I would have this. Now on the left, dq over dt, that's the rate of change in the charge, right? That's current, I, equals. Now over here on the right, the capacitance C is a constant. Once you manufacture the capacitor, once you decide on the metal for the plates and their area and their separation distance and the dielectric material inside, build the capacitor, you get handed that capacitor, the capacitance does not change. It's not a function of time. So I'll pull that out of the derivative operator, and we get this equation. This is the current voltage relationship in a capacitor. I'll label that as equation 2. And this equation, I like to say, I equals C dV dt. It rolls off the tongue beautifully. C dV dt. So that's one way of memorizing it. I equals C dV dt. Good. So of course, if you're given the voltage across the capacitor V, then you can get the current through the capacitor with equation 2. But if you're given the current through the capacitor and you want its voltage, then we need to solve this equation for V. So you should know from calculus that I can rearrange this a bit, and we'd say the voltage across that capacitor is 1 over C, divide by C, and take the running integral of the current. All right, so there are some interesting things going on in this equation, and depending on your comfort level of calculus, you may or may not understand what this equation is telling us. So let me describe it to you. For one, when you integrate something from minus infinity to a certain time, you are essentially accumulating or adding up from beginning of time to right now. So we are adding up all of the current that has traveled through that capacitor until right now, the time period that we're interested in. And of course, dividing by the capacitance. Second, you'll see that I've changed t to tau. And don't get too hung up on the tau here. This is what's called the dummy variable. Of integration. When I'm done integrating, I want a function of time. I want to know what is the voltage across the capacitor at a certain time. Okay? But when you integrate something, let's say from 1 to 2 x dx, when you integrate the x and plug in the bounds, it goes away. Right? So if we integrated this, we'd have 1/2 x squared from 1 to 2, and then we plug in 2 minus when we plug in 1. Right? So there are no x's there. It's not, this thing is not a function of x, despite what it looks like. It's a constant. So over here, we want a function of time. We want to know the voltage at a certain time. So we change the t's just to this dummy variable, tau, and then we plug in the current value of time. So there is our equation for the voltage. Now, this is kind of silly, this when time began at minus infinity. Usually, we know the voltage across the capacitor at some point in time, some reference point. We'll say that that reference point is t0. Okay? So let's say at time t0, I shorted out the capacitor, so I discharged it, and it had no voltage across. Well then, I would integrate from that reference point to the current time period. But I have to add to it the initial condition. What was it? What was the voltage at that reference point in time? Okay, this we'll call equation 3. And this gives you the voltage across the capacitor at any time t. Now we can say a few things about the capacitor based on equation 2 here. First thing I want to point out to you is that we'll change the wording in a second, but we'll say for now, when nothing is changing, or we'll say when V, the voltage, does not change, well, what's the derivative of something that's not changing? It's 0. So when V does not change, the derivative is 0 times whatever the capacitance is, and we get 0. I equals 0. Okay, that is to say, if V is not changing, we call that a DC circuit, right? Okay, and the capacitor acts like an open circuit. At DC. Open circuit because I is 0. It has no current traveling through it. At DC, DC means the voltage is not changing, the current is not changing, etc. So like a 9-volt battery is a DC source. It's 9 volts regardless of what time it is. The second thing we can say about the capacitor, based on equation 2, is the voltage V cannot change, and your book uses the word abruptly. That is to say, the voltage has to be continuous. If it's discontinuous, the derivative at the point of discontinuity is infinite. So that would make the current through the capacitor infinite. Well, that can't physically happen. And so the capacitor will prevent any waveform or any voltage that changes abruptly to be applied to it. So let me give you a couple quick examples of this. So let's say this is time, and this is voltage V. This waveform across a capacitor, we'll say this is 2 volts, maybe 4 volts, 0 volts. This waveform is not allowed. This has 2 discontinuities right here, the jump from 2 to 4, and this discontinuity, the jump from 4 to 0. That's not allowed. Cannot have that across a capacitor. Okay, let me show you one that you can have. Of course, you can think of many that are smooth and continuous. Okay, but let me show you one that you can have. You could have this. 2 volts, 4 volts, 0 volts. While this is not smooth, okay, it does not change abruptly. It is continuous. Okay, it's a continuous function. This is allowed, and certainly there are many more that are allowed. Now, if it's the job of the capacitor to store energy in its electric field, then we might ask, how much energy is it storing? All right. Well, energy is related to power, and electrical power is I times V, and we've already seen now that I is C dV dt. So this is C V dV dt. Okay, and then work, or energy, W, is the integral. It's the running integral of power, right? There's the dummy variable of integration again. So this is C times the integral from negative infinity to t of V dV dt, excuse me, dV d tau, okay, and this is equal to, so the d tau's cancel, and I integrate V dV, that's 1/2 V squared. So this is 1/2, excuse me, 1/2 C V of t squared minus V at minus infinity squared. Let me erase some of this. Let me rewrite this so it looks a little bit better. Again, this is 1/2 C times V at the time squared, that it is now, minus the voltage across it at the beginning of time. Now, when this thing was created, remember when we started this, we said that the plates are uncharged, so this thing is 0. And so the voltage, the energy is 1/2 C V squared. All right, well, let's look at a couple of concrete examples then. Again, feel free to pause these videos as we go. All right. So, for example, let's consider a 6 milliamp source. In parallel with a 3 kilo ohm resistor, a 2 kilo ohm resistor, 2 millifarad capacitor. And we'll have a 5 kilo ohm resistor there and a 4 millifarad capacitor here. And that branch in parallel with a 4 kilo ohm resistor. And the instructions would be find the energy stored in the capacitors. Find the energy stored in the capacitors. So first notice that we only have one source and it's fixed. It's 6 milliamps. So it's not changing, and this circuit then must be at DC. So at DC, the capacitors we can model as open circuits. No current goes through them. So let me replace the capacitors with open circuits. So I'll draw that in blue. Here's the new part of this. And I say the new part of this because now it's essentially a problem from the first 10 weeks or so of the course. Right? We need to find the voltage across the capacitors because the energy in the capacitor is 1/2 CV squared. So we are looking now for this voltage, call that V1, and this voltage here, call that V2. All right, so you might want to pause it right now, see if you can find those voltages. But here we go. Let's get V1 first. Now I want to point out to you that the 2 kilo ohm resistor and the 4 kilo ohm resistor are effectively in series, and that's because no current can come up here and no current can go down there. So the current through the 2 kilo ohm resistor has no choice but to go through the 4 kilo ohm resistor, making the two in series. Further, that series combination of the 2 and the 4 is in parallel with the 3 kilo ohm resistor. Right? So this 9 milliamps comes up here and it splits up. Some of it goes down, some of it goes to the right. Therefore, we can get the current here, call it I, using current division. So that current I is 6 milliamps times the branch whose current we don't want, 6 kilo ohms, divided by, 3 kilo ohms, divided by 3 kilo ohms plus the resistance of the second branch, which is the 2 in series with the 4. Like that. So this fraction is 1/3. 1/3 of 6 milliamps is 2 milliamps. So 2 milliamps comes through the 2 kilo ohm resistor. So now from Ohm's law, if I want V1, I've got a 2 kilo ohm resistor times 2 milliamps through that resistor. There has to be a difference then of 4 volts across that resistor. So that's V1. That's the voltage difference from this node to this node. Call that node 1, node 2. While we're at it, let's label the other nodes. Call this node 3, and this node 4. And let's ground node 3. Now, I can get the voltage from, I can get the voltage difference from 2 to 3, because I know that 2 milliamps comes through the 2 kilo ohm resistor and has no choice but to go through the 4 kilo ohm resistor. So the voltage from 2 to 3, I'll write it like that, is 4 kilo ohms times 2 milliamps. That's 8 volts. So that's the voltage again from 2 to 3. So if 3 is grounded, that means this is 8 volts up here. Now what's the drop across the 5 kilo ohm resistor? And I'll give you a hint, there's no current going through that 5 kilo ohm resistor. So no current means no voltage drop. So if node 2 is at 8 volts, then the other end of that resistor must also be at 8 volts. That means the voltage we're looking for, V2, is 8 volts. Again, pause the video if you need to. So, the energy stored in the 2 millifarad capacitor is 1/2 times 2 times 10 to the minus third farads times 4 volts squared. Right, so that is 16 milli, and what was the unit for energy? Joules. Okay, the energy stored in the 4 millifarad capacitor is 1/2 4 times 10 to the minus third farads times 8 volts squared, which is 128 millijoules. 128 millijoules, 16 millijoules, and we've got our answer. All right, so I'm going to clean this up a bit, and let's look at another example. Sorry, this is 20 microfarads. This is 30 microfarads. All right, and same instructions. Find the energy stored in each capacitor. All right, again, the only source here is that 50 volt source, and it's fixed, it's 50 volts. Nothing's changing in the circuit. So when nothing changes in the circuit with respect to time, that's a DC circuit. So at DC, the capacitors act as open circuits. Now the demo at the beginning of this video, I had this toggle switch, so that switched on and off the battery. So that is a change, and that's when you can start to see the effects of the capacitor. But we'll get there in a few lessons. Now we'll call this voltage V1, and we'll call this voltage V2. Again, now this is a problem from weeks prior. Find those voltages. Okay, well notice here this is a big series circuit. So the current that leaves the power supply goes through the 1K, then it has no choice but to go through the 3K, and then through the 6K and return. So that's a big series circuit. So we can get these voltages quickly using voltage division. So V2 is obvious. Let's start there. To get V2, that's the voltage across the 3 kilo ohm resistor. So from voltage division, we have 50 volts times the resistor whose voltage I want, divided by the sum of those 3 resistors. Okay, so this fraction is 3 over 10 times 50. That's 15 volts. Now V1 is simple, but it's slightly trickier. V1, let me circle the nodes so it's more obvious. V1 is the voltage from this node to this node. There's no single resistor that is connected to those two nodes, but the combination of the 3 kilo ohm with the 6 kilo ohm is, in fact, connected to those two nodes. So for voltage division, we want 50 volts times the resistor that we're interested in. So that's the series combination, divided by the total. So that's got the 1K in it as well. Alright, so this fraction is 9/10 times 5, so this is 45 volts. Alright, so now we're good to go. The energy in the 20 microfarad capacitor is 1/2 times 20 times 10 to the minus 6 farads times 45 volts squared. And the energy in the 30 microfarad capacitor is 1/2 times 30 times 10 to the minus 6 farads times 15 volts squared. Okay. Plug it into the calculator, see what you get. But that is the answer. Well, if nothing else, these last two examples have showed you, or at least reminded you, how important it is to be able to detect the series and parallel combinations of resistors. And so now I want to turn your attention to identifying and combining series and parallel combinations. Or let's just say combining capacitors. All right, so let's first consider parallel circuit. So let's say we have a current source I, and in parallel with that are N, so we'll keep this general, N capacitors. So we've got C1, C2, these are potentially different capacitors. And we'll say ... ellipses Cn ... All right, and we want to know how to combine those capacitors. And so over here I'm going to draw an equivalent circuit. So what would be CEQ in this case? What is CEQ? So let's first remind ourselves of what it means to have an equivalent combination. And that is, in this case, since this is a parallel circuit, we have one voltage to analyze or to find. And so we'll have a voltage here. And an equivalent combination means that if the current source is the same, so if the I here is the same as the I here, and if this is truly an equivalent transformation, then the voltage should be the same in both cases. So we've got two different circuits, the I's are the same, the V's are the same. We want to know what is CEQ. All right, so in this figure on the left, I comes up and it splits. So we'll call this I1, I2, and so forth, IN. And it's important to point out here that V does not get a subscript 1, 2, 3, etc. Because, again, this is a parallel circuit, so they all have the same voltage. It doesn't matter what branch we're at, it's still V, V, V. Same voltage, parallel circuit. All right, well, it must be true then, from Kirchhoff's current law, I is I1 plus I2 plus all of these currents, right, all the way to IN. And we can write this more compactly in sigma pi notation. Like that. Now we know that for capacitors, I equals C dV dt. So that must mean I1 is C1 times dV dt, and I2 is C2 dV dt, and so on. IN is Cn dV dt. Or, more compactly, J equals 1 to n of Cj dV dt. Now, since V does not have a subscript, it's the same for any branch, it could come out of the summation. Like this. Now let's come back to this in a second, but let's look at the right circuit here. Well, this one is simply I equals CEQ dV dt. Right? And remember what we said at the beginning of this, those I's are the same. So we can set these equal to one another. Here. And the V's are the same as well, right? So that term cancels, and we're left with that. The equivalent capacitance is the sum of all of the individual capacitors. C1 plus C2 plus up to Cn. And again, this is for parallel capacitors. So this should look familiar to you. This is exactly how series resistors combine. Right? They just add together. So parallel capacitors combine like series resistors. Okay, I'm not going to work an example here because I'm assuming you can combine series resistors, so you should be able to handle this equation. All right, well now let's observe series capacitors. All right, so here, this is the dual to the previous problem. Let's say we have a voltage source V, and we have N series capacitors. Over here, we have that same voltage source and an equivalent capacitor. Again, so for equivalence, same voltage source, and the circuit on the right has a current I. The circuit on the left also has that same current. And again, this time this current does not have a subscript. It does not depend on which capacitor it's going through, okay? Because it's a series circuit, they all have the same current. This time, the voltage could possibly be different. V1, V2, all the way to Vn. Now from Kirchhoff's voltage law, it must be true that V equals V1 plus V2 all the way to Vn, or more compactly, J equals 1 to N Vj. Now, as a side note, let's recall that the voltage across a capacitor is 1 over C times the running integral of the current through it, plus the initial condition. All right? Well, in order to compare these two circuits, we want to compare apples with apples. So we want to assume that they've all been charged previously to the same voltage. And we're going to just pick a number, and we're going to say that the initial charge is 0, just to make this analysis a little bit more simple. Okay, so we're going to assume that all of the capacitors here on the left and the capacitor on the right are all uncharged initially. So now, the voltage here is the summation J equals 1 to N of the voltage across the capacitor. So that's 1 over Cj times the running integral of the current. Okay. And the current, because this is a series circuit, does not depend on which capacitor we're talking about. So the integral can come out of the summation. Like this. Now over here on the circuit, in the circuit on the right, nothing fancy. We've got V equals 1 over CEQ times that running integral of the current plus the initial charge, which we're saying is 0. So this is the voltage. So same initial charges, 0, same voltages, so we can equate these two things. Okay, equate the two voltages, so I've got this guy, and the integrals on both sides cancel. Right? So I'm left with 1 over CEQ is equal to a sum of the reciprocals of the capacitors, which is 1 over C1 plus 1 over C2 plus all the way up to 1 over Cn, and then to get the CEQ, take the reciprocal of that, or the inverse of that. So that is how you would combine series capacitors. Again, this should look familiar. This is how you combine parallel resistors. All right, so in total now, series and parallel, capacitors combine in an opposite fashion to resistors. Again, I'm not going to go through an example because I assume you can handle this equation because you've been combining parallel resistors. I'm going to leave you with a couple of questions that you should think about. A couple examples. Let's say question 1. Let's suppose we had a capacitor. Let's say 1 millifarad. And then we took that 1 millifarad and in series with it, put a capacitor whose value we don't know. What can you say about the equivalent capacitance here as compared to the capacitance here, 1 millifarads? Is it the same? Is it less? Or is it more? Or does it depend on Cx compared to 1 millifarad? Second, let's take that 1 millifarad again. And let's now make a parallel combination. What can you say about the equivalent capacitance here as compared to 1 millifarad? Is the equivalent capacitance here the same, less than, or greater than 1 millifarad? Or does it depend on Cx? So I'll let you think about those two questions, and I'll give you a hint. The answer is the opposite of what the answer would be if these were all resistors.